Good morning, everybody. Has the spring break excitement started happening yet? No. Okay, just like, please make me no. How many of you have at least 2 exams this week? Yeah. Okay, 3. Anybody with 3? Had? Yeah, last week? Yeah, so I know you got my exam the week after you get back. Are there any more exams in the week you get back? Yeah, 3 that week. So you don't get spring break? Yeah. School's hard. School's worth it. You eventually get to a point where you realize school is easy and you want to get back to school, which is why I never left. All right. Let's see. Let's get these out. I think I forgot to give this to you for 3 weeks. Was this side of the room just section 1? Pretty much. Right, anybody with section 2? Back here. 11 a.m., right? All right. There is a quiz coming up as I promised, but I figured we'd warm up just a little bit before we got to the quiz by trying to remember what angular momentum is, okay? And then we're going to talk about how it gets affected in that. Okay, so angular momentum. Anything that's rotating has angular momentum, and as we're soon about to see, even things moving in straight lines can have angular momentum. So we have different ways of expressing this, right? We've got this general idea, right, that if you have any object moving with momentum, and that momentum right there, that P, that's linear momentum, right? So it's like the tangential speed something would have as it's going around in a circle. We know the radius, and we know the object's momentum, we know its angular momentum. And then if the distance vector, the radius vector, and the momentum vector are perpendicular to each other, like anytime we have pure circular motion, we can write this angular momentum as mvr. Notice I'm writing just the magnitude there because how are we going to find the direction of angular momentum? Got to use that right-hand rule, don't we? Okay. So if it's going in a circle, right, and let's say it's going around with angular speed that way, which means, right, at any given point we'd have a tangential v like this. Shouldn't draw that one over there, right? So far you've learned 2 right-hand rules. You've learned a hitchhiker and you've learned a finger pointer, right? So which right-hand rule can we use to find the direction of angular momentum for this object going around a circle? Actually, the answer is both. Okay? So using the hitchhiker, what would we do? What direction would we get if we use the hitchhiker? Finger wraps around in direction of omega, and my thumb is now pointing which way? Into the page, right? Okay, so how would I use finger pointer? Well, I have a V, right? If I look at the tangential V down here at the bottom, I have V to the left, okay? Sorry, it's R cross V. We do R first. So there's our radius, okay, coming down. So I put my finger down. I make sure that my middle finger is pointing in the direction of velocity, which is to the left, and that leaves my thumb pointed which way? Still inwards, right? And it doesn't matter where you do it, right? If we do it on the right-hand side, R, okay, and then I've got to turn my hand. Sometimes you got to turn your body, right? So R, V going up, which way is the thumb pointing? Still in. If I do it at the top, same deal, right? So the hitchhiker becomes sort of a quick way for anything that's moving in circular motion, right? Anything that's rotating. You can find its angular momentum. But you can still get it from that cross product thing. Okay. And then, as I already showed you, and this has to do with rotating rigid objects, meaning things that are more than point particles, okay? We can also, so we've got this, which comes from that. We can also do I omega. And here I can put the vector signs on it because the direction of angular momentum is the direction of angular velocity. And that I right there, what is that? Yeah, it's the moment of inertia. And so what does that mean you need? Need the table, right? Because we can find the angular momentum of any of these objects, right? We can find their moment of inertia and how fast they're rotating. All right. So let's do an example of finding the moment of inertia of a rotating rigid object. We're going to do the clock face of Big Ben. Who's Big Ben? You're Big Ben? Here's Big Ben today. Okay. Big Ben is the famous clock tower in London, England. Okay. Kept time for all of London until pocket watches were invented. Right? Okay, and it still works, of course. I think it's undergoing renovations right now. But it's pretty big. I mean, this picture doesn't do it justice, right? But this clock face is many tens of feet big, right? Several meters. And so we're going to find the angular momentum of the face of Big Ben. Now, one of the things I failed to put into this problem for some reason is the length of the minute and hour hand. So let's see, the length of the hour hand is apparently 2.7 meters long. So almost 3 meters, which is about 9 or 10 feet long. Right? We'll call it 9 feet. And then the length of the minute hand is 4.5 meters. So that's a good 12 feet right there. Right? These are pretty big. Dude, I like, let's see, 4.5 meters. So it'd be from here. So roughly about there. That's the minute hand, right? On Big Ben. This is a big clock, right? And there's 4 faces all the way around the top. All right. Do we know how fast? So we want to find the total angular momentum of the face of Big Ben, one of the faces of Big Ben. And the way we're going to do that is we're going to add together the angular momentum of each, the hour hand and the minute hand separately. So we need to find the angular momentum of the hour hand, angular momentum of the minute hand. And when I say add them together, I mean add them together as vectors. Angular momentum is a vector. And so that means we need to find the vector direction. So to know whether or not we're actually like adding them together or maybe subtracting them. So how do we find the angular momentum vector of the hour hand? On a clock face, which way, and I know I'm like, aging myself here by referencing these ancient things called clocks, right? But which way do the hour and minute hands move on the clock face? Clockwise. So we take our hands, wrap them around the clockwise direction. Which way does our thumb point? Points into the screen. So I've got these 2 hands, right, on the clock face. And by the way, which one is the hour hand and which one's the minute hand? The smaller is the hour hand, okay? The hour hand is our minute hand, right? They're both going around clockwise, of course, where we get that, right? So both the angular momentum, right, for the hour hand is into the page. So what does that mean we're going to do to these separate angular momentum? They're both going in the same direction. We just add them together. We're not going to subtract them, right? Okay. So we've established that, and so from here on out, I'm just going to kind of drop the signs. I know what direction they're going. I know I'm adding them together, so I'll take care of that at the end. So now we need to find the angular momentum of the hour hand. We got sort of these 3 ways, right? We can do a cross product, R cross P. Or we can do MVR or RMV, right, for a point particle moving in a circle, which I don't want to do the cross product. And is a minute hand or an hour hand a point particle moving in a circle? No. They're extended, right? They have mass that goes everywhere. So we're going to use I omega. Moment of inertia of the hour hand times the angular speed of the hour hand. Okay. First thing to conquer is an hour hand anywhere on this chart. Is there a shape that's even close? D? All right, so yeah, Mason's going straight for the sort of engineering answer here, right? Because it looks like, but like, I guess we could scale A and B right out, like if we knew the dimensions of the hour hand, but all they told us was the length. They didn't give us a width. So we're going to have to sort of approximate here. And so is there something better than D? Yeah, A and B are close, aren't they? But what's the key difference between A and B? Where they're rotating around, right? And does an hour hand rotate through its center? No, it's attached at one end, right? And rotating around. So that means B is probably the best choice that we have here. And again, Mason, if we had like width and dimensions of the hour hand, we could then do better with D. But we'll stick with B. We'll stick with B and go from there. So we're going to use, and I forgot to read it. Was it 1/3 ml? 1/3 ml squared, right? So we'll use that for both the hour and minute hands with their masses and lengths. So let's just get them both, right? It's going to be 1/3 times the mass, which is 60 kilograms times length of the other, 2.7 squared. I got 146 kilogram meter squared. And then for the minute hand, same equation, different numbers. 4.5 meters squared. And I got 675 kilogram meters squared. All right, so there we go. We got them both. And of course, we're going to find the angular momentum of the minute hand by doing exactly the same thing, but with all the minute hands data. All right, so what about angular? Did they give us the angular speed? Do we know, can we find omega? Yeah, okay. So what do we know about how fast, in terms of angular quantities, an hour hand goes? So an hour hand goes around the clock face once, and how long does it take to do that? 12 hours. The answer is not 1 hour, right? It's 12 hours. So the hour hand does 1 revolution every 12 hours. That's its angular speed. Can we use revolutions per hour in calculating anything? It's a non-standard unit, right? What are the standard units for omega? Radians per second, right? So we got to get this into radians per second. So what do you want to convert first, the revolutions or the hours? Revolutions? For every 1 revolution, there's 2 pi radians. Okay, so that one's done. We get to cancel out both of the revolutions and get to radians. And in 1 hour, there are 3,600 seconds, right? 60 minutes in an hour, 60 seconds every minute. So that's 60 times 60, which is 3,600. All right, so there we go. We got to do 2 pi divided by 12 divided by 3,600, which, if I did that right, is 1.45 times 10 to the minus 4 radians per second. Pretty slow, right? So slow that it's kind of hard to see it move if you're just staring at it. All right, same calculation for the minute hand. Different data, okay? So it does 1 revolution. So the minute hand, how long does it take to go around once? Not 60 seconds. That would be the second hand. Every hour, right? Okay. So 1 revolution for every hour. And again, 2 pi radians per revolution. And then in 1 hour, 3,600 seconds. And I forgot to cancel my units over here, but revolutions, hours, I'm left with radians per second. That's exactly what I wanted. And we get 1.75 times 10 to the minus 3 radians per second. So with these angular speeds, I don't expect there to be a whole lot of angular momentum, right? Okay. Angular momentum to be sure, but not a whole bunch. And the whole point of showing you this problem is that angular momentum can be added together. You can combine it, right? And so if you have a structure that's made up a lot of different things, they're all spinning differently, you can find the total angular momentum by adding up all the pieces parts. Okay, so now we take angular momentum of hour hand and minute hand, and so that's going to be I hour, omega hour, plus I minute, omega minute. And now I just toss in a bunch of numbers. 146, and I got to get them all in the right spot, right? 146 times 1.45 times 10 to the minus 4 plus 675 times 1.75 times 10 to the minus 3. And kind of, this is the part where you are allowed to just sort of hope and pray that your calculator behaves, right? Everything up to this point has been human, and now machine's gonna get in the way, and it's just gonna be bad. Speaking of which, I'm not too worried about my job because I got onto the testing branch of the Bing AI search. You guys know about this, right? Where they put Chat GPT together with Bing, right? It doesn't do physics well at all. I've been feeding it your homework just to see, right, what it comes out. It's interesting. It will get like a lot of the physics right and then completely blow the answer in terms of like a numeric calculation. It's a large language model, which means that the AI isn't so much an intelligence as it is a statistical predictor of like what words go together, right? And so but it can do the statistics really, really fast, so it makes it look like it has artificial intelligence. Anyway, it's pretty hilarious. I fed it one of your chapter 11 homework problems just this morning, and it got like part A, like it explained it correctly. I was really impressed that it got the concepts, like you had to do energy and this, that, and the other thing, and then it completely biffed the numerical part. Like it just. It made up numbers. It didn't look like it didn't even bother to calculate the formula it had derived. And then for like part B, it completely messed up. Like it just went completely off the rails. I mean, it wasn't doing like poetry or anything. It was still doing physics, but it was wrong. So yeah, beware of Bing. Although ChatGPT apparently version 4 now has a plugin for Wolfram Alpha. So I haven't seen that in action yet. I don't have access to Chat. I only have access to Bing. I don't have access to ChatGPT because that costs money. All right, that was that. And as you can see, not a terribly large number, but I don't expect it to be terribly large because those hands aren't moving that fast. Yeah.
Does a moment of inertia only apply to angular momentum, or also to linear motion?
So, we're about to get into this, right? Moment of inertia is involved anytime you have mass rotating with it, right? Now, what does it mean for something to rotate? You can have rotation about a point in space even when something is moving in a straight line, right? If you have a point that you're referencing, you're saying, okay, is that rotating? Well, it's rotating, but the radius is changing constantly, right? We tend to think of rotation as being pure circular motion. That's not the only kind of rotation you can have. I'm kind of glad you asked that question because that segues very nicely into our quiz. Okay. Let's talk conservation of angular momentum. We did conservation of momentum before, right? Now we're going to do conservation of angular momentum. And when we did conservation of linear momentum, things moving in straight lines, right? We wrote that down where we said whatever we start with has to be whatever we end with, right? Using the simple P for linear momentum. We did have two different kinds of collisions. A little review here for you, right? A little taste of what you have to do when you get back to straight line. Okay. We had two kinds of collisions. We had elastic and inelastic collisions. The big difference being that inelastic is when things stick together or there's deformation, loss of kinetic energy. All right. When it comes to conservation of angular momentum, we have the same statement. It's just we don't use P, we use L. Whatever you start with has to be what you end with. The problem is that when we did linear momentum, there was this concept and idea of the collision. There were two objects coming in and interacting with each other in a linear way, like along a line. And so, what does a circular collision look like? If you have a picture in your head right now, chances are it's completely incorrect. Okay? Because what you might be thinking of is maybe two wheels rolling towards each other and bouncing off. That is not a circular collision. That is a linear chapter 9 collision because the center of masses are just moving towards each other and bouncing off. Okay? What's that? So like bumper cars? Like kind of
rotating into each other.
Like spinning like this? Like doing donuts into each other? Or okay, like turning into each other? In the moment of the collision, it's still linear. Yeah. It's really hard to think of what a rotational collision is.
What's tetherball the example?
What?
A tetherball pole?
No. Well, yeah. You're getting much closer. You're thinking. So, are you thinking of like when they hit the ball,
Yeah.
or when the ball wraps itself around the pole and the string gets shorter and shorter? Whichever one is right is the one I was thinking. If it's the kind of tether ball where the ball wraps itself around the pole, gets shorter, and you know that you win, right, when it hits the pole, right? Then yes, the entire time it's wrapping itself around the pole could be considered an angular collision. Good one, I like it.
Like planets colliding or black holes, how they spin around.
There's rotation involved, but in the moment of the interaction, that is still a linear problem. There's a difference between these three and the tether ball. A key difference. And it all has to do with what is changing.
The radius.
Okay, so if the radius of the tether ball is changing, what circular thing is changing? Well, the angular speed changes because this other thing is doing the collision, the change. Yeah, but what does that mean is changing? It's moment of inertia. Because the moment of inertia of the tether ball, mr squared, it's a mass at a distance squared, as that r gets smaller and smaller, the moment of inertia is decreasing. And so if we're going to conserve the angular momentum and have what we started with at the end, really, this is all about changing moments of inertia. So in circular collisions, I'm using that word collision very loosely here. In a circular angular conservation of momentum, that was redundant, you want to look for changes in moments of inertia. If the moment of inertia of a rotating system changes its angular velocity is going to change. So, I brought with me my Michel Kwan simulator. Does anybody know who Michel Kwan is anymore?
The ice skater.
The ice skater, okay? World famous, won all kinds of world championships, amazing figure skater. She never won the Olympics. Okay? And yet is one of the greatest skaters of all time. Tells you something about the Olympics. Anyway, why is this my Michel Kwan simulator? What's one of the things figure skaters do during their routines? Very famous move. They'll spin on the point of it, right? Okay? But the move always involves a beginning move, okay? Where they're like skating and they're kind of going around the ice rink and they've got their hands out, right? And they've got their foot out, right? Okay, like this. My core is not where it needs to be, right? Okay? And they're doing this, and then as they get to the end of this move, what do? They pull everything in, right? They stop moving forward, and they take that forward momentum, and they turn, right? And they start spinning, and as they pull their arms and hands in, what happens to the speed of rotation? Speeds up, doesn't it? And then they'll do all kinds of things where they'll kind of take their arms in and out and all that kind of stuff. And as they put their arms and legs out, they'll slow down, and as they pull them into the center, they'll speed up. What are they changing? Their moments of inertia. So I brought my Michel Kwan simulator here. It consists of a stool that rotates on a fairly frictionless bearing, right? Okay? And 2 5-pound weights, okay? That'll hold out at arm's length. I'm going to put myself into a spin, and then I'm going to pull my hands in, okay? What's going to happen to my moment of inertia? Bigger or smaller? Smaller. Why is it going to get smaller? The radius where these masses are is going to get a whole lot less, isn't it? Okay? And so, by conservation of angular momentum, right? If I solve this, I put the right subscripts on things. If I solve this for my omega final, right? If my moment of inertia final is less than my moment of inertia initial, I've got a smaller number in the denominator than I do in the numerator. What happens to that ratio? So you get bigger or smaller than 1? If the denominator is a smaller number than the numerator, what happens to the overall thing? It gets bigger. So I'm going to have a bigger number times my initial. In other words, my final will be a big number bigger than 1 times my initial angular velocity, which means that I should speed up. Let's see what happens. Going. All right, and pull them in. Whee! Throw them out. Okay, slow down. Go the other way so you don't get dizzy. Physics is dizzying enough, right? Try lecturing while you're dizzy. It's kind of fun. All right, so when you're up against a conservation of angular momentum problem, there's going to be a change in moment of inertia. And you're like, well, Mr. Balogh, outside of figure skating and tetherballs, when does this happen, right, in nature? Well, fair question. Like, that's always a fair question. You should always just pin scientists down and say, when does this happen in nature and why is this important, right? Okay. So I have another example. We're going to get back to this and we're going to do a calculation of this here in a second. But I want to underscore, right, that this is a lot more common than you realize. I know this looks a little bit big and scary, okay? But what is this a picture of? It's a transmission up there in the left, okay? And down here on the right, that's the clutch. Okay. So, how does your car go? Okay. Your car goes by turning key, push pedal, turn wheel, right? Car go. But if we get down into the nitty-gritties of it, okay, your engine in your car needs to be connected to a series of gears that allow the car's engine to be efficient in how it utilizes its power. If your car had one gear, okay, what would happen is the revolutions of your engine would have to be extreme at high speeds, okay, and small at low speeds. What you want, and you probably have experienced it as you've accelerated, say, onto the freeway, does your car kind of go, right? You can feel it, you can hear it, it's shifting gears, okay? And each of those gears allows for the engine to run slower and yet maintain the speed of the vehicle. And slower running engines run cooler, use fuel more efficiently, etc., etc. So, in order for your car not to explode every time it shifts gears, okay, because it's got to go from like high to low, right? But it also has to be able to go from a stop, not moving at all, to going. And some hybrid cars do this a little differently, but a standard car, right? When you're sitting at the stoplight, is your engine on or off? It's on. Your engine is turning, okay? There's a big flywheel in there, and it's constantly turning, and the engine's idling, right? And when you take your foot off the gas and put it on the brake, you have to take the part of the engine that's turning and connect it to the rest of the car that isn't turning. And if you didn't have a mechanism for connecting those two parts smoothly, your car would go, right? Now, you don't have to raise your hand, and I know it's a dying art form, okay? But some of us learn to drive manual transmission, okay? And in the manual transmission car, there are 3 pedals, right? Because everybody has 3 legs, right? What's the 3rd pedal for? It's called the clutch. And it's the pedal that actually engages and disengages 2 spinning discs. One disc that's connected to your engine rotating around, and the other disc which is connected to the rest of the wheels of the car, right? And if you're at a stoplight, you've got your engine turning around and you've got the wheels not turning, right? Okay? And when you want to go, you need to get the 2 to start moving together smoothly, right? This is an angular collision. Something that's rotating, something that's not rotating. This has a moment of inertia all its own. This has a moment of inertia all its own. Initially, this is the only one spinning, but now we've brought 2 of them together, changing the moment of inertia of the system, right, as it goes. In an automatic transmission car, well, the car does this automatically, okay? In a manual transmission car, you have to learn how to use that clutch pedal in such a manner that you don't stall the car. You can like take the clutch off too fast, and the 2 parts come together too quickly, and there's not enough torque for the motor to overcome the sudden change in moment of inertia. The car's engine will stop, okay, as a way to protect itself from dying, okay? Or if you ride the clutch pedal, okay, meaning that you kind of depressed it, and it's not fully disengaged, it's not fully engaged either. The springs in here, you're changing the spring tension, and the clutch plates are sort of slipping and sliding against each other in bad ways, and you can kind of like glaze the clutch assembly so that it, every time you engage it, it sort of slips, okay? That's not good either. My dad did have to change the clutch in our car when I started learning how to drive. Everybody makes this mistake, okay, learning how to drive a manual transmission car. And I also learned, I love my parents. My parents are fantastic people. My dad thought it'd be a good idea to teach me to drive in San Francisco. We lived about 90 minutes from San Francisco. And he's like, yeah, we're going to go learn how to drive. And so we drove to San Francisco, where the streets are like this, right? Okay, and all of them have stop signs right at the topmost point, like the street's doing this, and it does have a little flat section at the intersection, and they put the stop sign right before the flat section. Like, you could have designed San Francisco just to, like, maybe 1 or 2 cars could fit up there. But no. You've got to, and as soon as you let go of the brake, what's your car going to do?
Slow down.
And so you have to do like 3 pedals with 2 feet. It's really fun. Nowadays. It wasn't fun back then. Anyway, where was I? Oh, let's do the example of this, right? Doing an actual calculation with conservation of angular momentum, okay? So we've already fleshed out, right, sort of the process here, okay? But we gotta think about, like, what is the initial moment of inertia, and what is the final moment of inertia, and what's changing? So let's we need the table, right? If we go back to the table, is there an entry for Mr. Balogh? Be careful, your grade depends on not picking anything that's a sphere. We could model Mr. Balogh as like a cylinder, maybe, right? Okay, certain mass, right? Certain radius, right? Okay. Or we could go measure Mr. Balogh's moment of inertia. Okay? And what's the way of measuring the moment of inertia of something? Well, spoiler alert, you'll be doing it tomorrow in lab. Okay? We're going to be applying a torque to a rotating object, and from that information, we're going to be able to find the moment of inertia experimentally. So let's say we go and do that. I know I didn't explain that process to you yet. We'll do it tomorrow. But let's say that the moment of inertia of Mr. Balogh, okay, is measured and found to be 3 kilogram meter squared. So that's just me, right? But that's not all, right? We've got these masses that are sitting out at a certain distance, okay? So what do we do about all of this structure, okay? So what about this? Do we need to worry about this? Physics muscles, massless arms. Let's keep it simple, okay? And we'll just concentrate on the 2 masses out at the ends of my arms, okay? So we'll say maybe the 3 is an average for my arms and my trunk. We're just gonna focus on these masses right here, okay? Right? So how do we find the moment of inertia of a mass, just a point mass? It doesn't have any structure out there, right? Going around in a circle. Yeah, that one's not on the table, right? You might want to pencil it in on the table. If you've got a point mass that's going at a radius, it's just mr squared, which is the definition of moment of inertia, right? Confusingly, mr squared also happens to be the same as like a hoop, right? Which is a big ring of masses all the way around. But same equation, different applications. So, the moment of inertia initial, right, is going to be the moment of inertia of Mr. Balogh's trunk, right, the central thing, and we'll include the chair, right, that's all lumped together in this 3 kilogram meter squared, plus the moment of inertia of mass 1, plus the moment of inertia of mass 2. Like, there's a total moment of inertia here, right? Everything put together, okay? So I got this one, I got this one. Now, luckily, if we find the moment of inertia of this one, what's the moment of inertia of this one? If they're the same mass, it's exactly the same, right? So we could just come in here and say, well, you know what? Let's make this even simpler. It's twice the moment of inertia of one of those masses out there, okay? And we're gonna use the moment of inertia of a mass is just going to be mr squared. So the initial moment of inertia is Mr. Balogh plus 2 times the initial moment of inertia of the mass. I'll put initial up there, and then I'm just going to put in mr initial squared. Again, where does the 2 come from in the front of that thing? There's 2 masses, right, at exactly the same radius. We'll assume Mr. Balogh's arms are symmetrical in their length. And then the final moment of inertia is going to be exactly the same thing, only a different radius. So, putting this all together, we can calculate what these two things are, right? Moment of inertia initial is going to be 3 plus 2 times the mass in my, let's see, in my, what did I use? I used 2 times, are they 3 kilogram masses? They must be 3 kilogram masses. I should write stuff like this down. 3 kilograms. That's a little bit more than 5 pounds, but it's close enough. 3 kilograms. Okay, and then what should we say the initial radius is? About 1 meter. Keeping it simple. We're guessing all these numbers anyway, right? Squared. So radius initial is 1 meter, and the mass is 3 kilograms. Okay, so what does that equal to? That looks like 9, doesn't it? 2 times 3 is 6, plus 3 is 9. So it's 9 kilogram meters squared. Okay, what's the final look like? Well, again, it's the 3 from me and the stool, plus 2 times 3, and like if I just kind of bend my elbow, right? It's looking like from the center here, maybe 30-ish centimeters, give or take. Maybe a little less. We'll use 30 because it's 0.3 squared. So we're saying our final is 30 centimeters. At least that's what I have in my notes. I got 3.54 kilogram meter squared. Okay. And let's say, how fast was I going initially? Like 1 revolution every 2 seconds, maybe? About. So my initial angular speed was 1 revolution every 2 seconds, or 1/2 revolution per second. Now we could put that into radians per second, but we don't have to. Look at this result right here, right? If I put the angular speed in as revolutions per second, what unit am I going to get out for angular speed? Revolution per second. Because what happens to the units of the moments of inertia? They cancel each other out, right? We're dividing them into each other. So just make sure your units for your moments of inertia are the same. Then you'll be safe. After that, it doesn't matter what your angular velocity is. Revolutions per minute, radians per hour, whatever, it doesn't matter. So, calculating this out, I'm going to get my initial, which was 9, over my final 3.54, times my 1/2 revolution per second. And I did not do this. I said 3/4 of a revolution per second, which isn't right. So. Slower than I thought. 9, 4, and 2. I got 1.27 revolutions per second. So my final angular speed was bigger than my initial angular speed as we predicted. Right? So conservation of angular momentum problems, you're looking for a change in moment of inertia. Okay? Either that change is being brought about because some radius is changing, or maybe you're adding on additional mass that needs to be calculated into the moment of inertia. Whatever the case may be, make sure you're concentrating on those changes in angular, in moments of inertia, and then finding your angular speed. All right. Now, all the examples I just did involved angular momentum changes that conservation of angular momentum, concentrating on that moment of inertia. But angular momentum is conserved and is a vector. Which means not only do we need to have the same amount before and after, if we lower the moment of inertia, we have to increase the angular speed, or vice versa. We also have to conserve its direction. So if your angular momentum before the collision, before the change, and your angular momentum after, they have to point the same direction, even if there's been a reversal of direction. Let me demonstrate. Okay, we got the big physics wheel now. Okay, so is this a normal bicycle tire in terms of like its weight or anything? No, this is very different. This is very heavy, but I point this out. Pick a strong person, right? Because I don't want you. I am weak. I admit that. I don't lift. Okay, but holding this thing up takes a lot of strength, right? And it's not insignificant. Okay. Especially because this is like solid rubber, and I think they've injected a little bit of metal. But we've also added these lead weights around the outside. Okay. And why are we doing that? What do we want to make as big as possible on this wheel? The moment of inertia. Okay. Because angular momentum is all about moment of inertia, isn't it? Okay. So what I'm going to do is I'm going to spin this wheel up. I'm going to use the Dremel. I'm going to get it going nice and fast. Okay. So it's going to have a lot of angular momentum. Okay. I need you to have your right hands ready. Okay. So let's see. I think maybe it'll spin this way. So if it does, I'm going to try to orient it like this. So I want to orient it like that. I want it spinning this way. So what direction is the angular momentum pointed if it's rotating like this? It's pointed up, right? You take your right hand, wrap around, and your thumb is pointing up. I'm going to, with it pointing upwards, okay, I am then going to get on the stool so that I can freely rotate. Now, what is my angular momentum initially? 0. And all of the angular momentum is going to be in the wheel, right? I am then going to reverse the direction of the angular momentum. Which way is the wheel's angular momentum pointing now? It's pointing down. So, I changed it, right? Initial is not equal to final. So there must be a change in angular momentum somewhere else. I want you, with your right hand, to see what my angular momentum is after I do the flip. Okay? Figure out what direction. I'm going to go right back. I want to get the face shield. I don't like really fast things spinning near my face. Knowing me, I'll be clumsy enough and put it right in there. All right. So we can make it work. Which way is it going? Okay. Is it going up? Yeah. You ready? Here goes. Which way is my angular momentum? It's up, isn't it? So this thing started up, right? And the system, even though I had now pointed this one down, the system maintained total angular momentum upwards. Angular momentum must be conserved in both its magnitude, the numbers, as well as the direction that it was pointing. Angular momentum wants to be conserved in its direction so badly that it will fight any change in that angular momentum. I love the sound this thing makes. I'm doing that. All right. let's see. Let's really care. Which way was that spinning? That way. Okay. So angular momentum is now pointed towards you, right? If I try, this is no exaggeration. If I try to move it, it tries to give me angular momentum. Ah. Rob, you ready? Are your shoulders okay?
Sure.
Okay. I'll help you. Don't move it real fast, but just try to like change it where it's pointing. What does it do? it fights, doesn't it? Like it literally, like you try to turn it this way and it goes no. Right? I have to like get a wide stance here, right? Okay? Because if I, right, it just goes over. Okay? And what's more, and I've already demonstrated this last time. What's more, it will fight that change so much that it won't fall over. You remember that last time I was hanging from the chain? Right? This is called gyroscopic procession. And I am literally like, I'm just holding on to the very end of the wheel, right? I'm not going to pass it under my leg. Holding on to the very end of the wheel. And do you see how it rotates around like that? Okay? Well, that's because there's a torque that's being applied to this. In Newton's second law, in rotational terms, right? Torque, okay, is equal to I alpha, just like F is equal to MA that we did in a linear term. There's another way to write this. This can be a change in momentum in time. In a similar way, this is a change in angular momentum in time. So, if a torque's applied, it will change the angular momentum. Angular momentum doesn't want to change. It'll try to fight it, but it doesn't have any choice. Where's the torque? Remember, I'm supporting it at one end. So what's causing the torque? Gravity, right? Center mass is over here. So gravity tries to pull it down. But that's not how torque works, right? Here's the support. R is to the left. Gravity is down, right? And so that means the torque is going to be along the horizontal. And that torque will cause the angular momentum to change. Anybody that's ever operated a leaf blower, okay, knows that you cannot turn while you're wearing a leaf blower. One of the big ones on your back, okay? Because a leaf blower, among other things, is just a really big circle, big fan on your back, okay? And when you go vroom with it, right, to make the air go fast, right, what happens to the fan in that backpack? Spins up, right? And now that fan has angular momentum pointed basically directly perpendicular out of your back. And what happens if you try to turn while that fan is going? It's going to fight you, right? And so you'll watch somebody using one of those, right? They'll have their control in their hand, and they'll walk in like perfectly straight lines, right? You won't see them turning very often, right? And if they want to turn, they'll let off the gas so they can turn. And that's why the hose is able to sweep back and forth. Because if you try to sweep back and forth with your body, you're in for a big workout. Okay? For the home user that doesn't want a big backpack version, you just want one of those handheld doobly-doos, okay? It used to be that they mounted the fans in those vertically like this, okay? And so in your unit, right, as you're using, of course, smaller circle, but still has angular momentum, right? What happens as you try to sweep the leaf blower side to side? You're fighting the angular momentum of the fan blade in that thing, right? And so people came back and complained about wrist fatigue and all kinds of stuff, right? Oh, I don't like using this thing, it fights me, whatever, right? So designers went, okay, well, let's put it this way, right? Put the fan so that it's horizontal plane. And now, as the user sweeps it back and forth, do they have to change the direction of the angular momentum vector? Right? And so there's no torque applied, and it's much easier to use. I'm an awful person. By nature, I try to be nice, but I have a bit of a mean streak in me. And one of the ways that the mean streak comes out is that I like to ask really hard questions of the poor people that work in big box stores. Right? Because I found that, well, if I'm going to buy something or anything, I'm going to research it. My training is research, data, comparison, statistics, right? So if I'm going to buy a bolt, by golly, I'm going to know everything there is to know about that bolt. It's a sickness. I understand. It's part of who I am. So I'll go in the store and I'll ask them specific questions about bolts or lawnmowers, whatever it is I'm looking for, right? Okay, and the poor person's face is always just like, because I've gone straight from, does a lawnmower have 4 wheels, to what's the gauge of the wire that you're using to connect the spark plug to the doobly-doo so that the thing doesn't break? And they're like, security, right? So I walked into one of the big box hardware stores. I won't name which one to protect the innocence of the people who work there. I walked in, and a poor young man came up to me, all eager, must have been fresh out of his customer service training or something, right? Came up to me and, can I help you, sir? Right? Nice, friendly. Okay. I said, yes, I'm looking for a leaf blower that maintains its angular momentum vector. What's that? Right? Now, he started, the shocked look on his face. It wasn't in the pre-programmed responses that he was taught in his human resources training. And he's like, what? And in that moment where I just secretly, inwardly was going, yes, I can teach a physics lesson right now. You know how those big box stores, they like just have the shelving, right? And they put all the stock up above and all the display stuff underneath. And sometimes you can like see through the display, right? And witness all the marital arguments that are going on in the aisle next to you, right? Okay. Well, this one you couldn't quite see through, okay? But you could hear, okay? And in that pause between me stating I want to maintain and the confused look on this person's face and the inhalation of breath I was taking to deliver a Nobel Prize winning lecture on conservation of angular momentum, I heard through the other aisle, he wants one with the fan mounted horizontally. What? Who said that? Who is the genius that works in this store? And around the corner came one of my 4A students that had that lecture like 3 weeks before, right? Okay? Just big old smile on his face, proud as can be. Hey, how you doing, Mr. Balogh? Right? It's like, gold star right there. Awesome. I also asked for 1 Newton hamburgers. Because what's 1 Newton? Quarter pound. Here's a video for you of something I'm not willing to attempt. And the people in this video have doctorates, and yet they don't do basic things like safety.
I am here at the University of Sydney, where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a meter-long shaft. Can you imagine trying to hold this out horizontally with just one hand at this end? It is impossible, okay? Now I'm gonna let go. You're able to hold this at all?
90 pounds.
Can you lift it out? Can you horizontal hold it? Hold it. Come on, just try to, I want you to hold it out horizontally. Hold it. Oh, come on. What I'm going to do is I'm going to spin this up to a few thousand RPM, and then I'm going to attempt just that. Hold it from one end and have it out horizontally.
No helmet, no armor. There is a lethal amount of energy in that spinning disc.
When I let go of my left hand, what you'll see is that the shaft remains horizontal. You can see it going around there.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic procession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme.
I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck.
But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning.
Let's prove that I can lift it just this end without it spinning. Here we go. I mean, it's just kind of awkward with the hand.
Careful. Physics muscle.
Woo, just barely. Oh, goodness. Do you even lift? Clearly, I do not.
Undaunted by my lack of strength, I'm going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the
There
best
are
chance
about
of success.
the equivalent of about 10 9mm rounds fired out of the gun. And that wheel.
4, 3, 2, 1, go. That was perfect. Now I am going to release my left hand and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1. Beautiful. Let's go again. In 3, 2, 1. Nice. 3, 2, 1. It feels incredibly light as I do that.
Without a helmet. So, Dr. Mueller's videos are great, by the way. Veritasium is a channel. You should go check it out. He does a lot of really cool things. Every once in a while, he does something really stupid, but it's still accurate. So, I want to leave you, okay, in preparation for your homework, just to kind of outline conservation of angular momentum problems. We talked about how the moment of inertia changes, right? When two spinning things comes together. You have a homework problem that's similar to a problem that we have whenever anybody walks through a door, especially one of those like spinning doors that you might see on the front of big buildings, okay, where people start walking around in a circle. You have a case where you have something that's moving in a straight line, contacts the door, and begins rotating. So from a top-down view, you might have the door like this, right? And the person comes in and connects with the door, right? So just like moment of a conservation of angular momentum before, you got the sandwich. You have what's happening before, you have what's happening after, and then you have what's happening during when the two things are coming together. So as that person walks into the door, if we take our axis, right, our point P, so to speak, right, we learned that even moving in a straight line, that person has angular momentum about point P. And in the instant they contact the door, we've got a 90-degree angle. And so we can calculate, we can find the initial angular momentum of this person using MVR. We know the speed at which they are traveling, right, as they come in and contact the door. Now, how much angular momentum does the door have initially? 0, it's not rotating, right? So we start with MVR, that's all we have to begin with. But when we're done, we have both a door and a person in rotation. They're going to be rotating at the same speed. Their omegas will be identical. And so we think of them as a combined object. The moment of inertia of the person plus the moment of inertia of the door times whatever angular speed they might have. And the problem probably is going to ask you to find the angular speed or something like that. Okay? I think your problem is a bullet gets fired into a pendulum and starts rotating or something like that. So the moment of inertia of the person is just going to be mr squared, where r is the radius of the door. Again, it's a point mass starting to move in a circular motion, so we just use mr squared. What would we use for the door? Probably the chart, right? Okay, and this one I think is going to be like 1/12 ml squared. I know there's dimension to the door, but that's captured in the mass of the thing. If you want to use the plate one, you can use the plate one, right? But the idea here, right, is that we start with angular momentum, we end with angular momentum, even with something that's moving in a straight line to begin with. In the instant of that contact, we can define an angular momentum about the axis of rotation. So when you see things moving in straight lines, if they're not moving directly towards or away from the axis, the point of rotation, chances are you're going to be able to write down an angular momentum for it. I will see you tomorrow, where we will measure moments of inertia in lab.